Hi, everyone. My name is Jack Deneau, and I'm working with Luke Bonvor, Kimberly Doyle, and Zach Woods on a project involving the wind tunnel performance of thin cambered plate airfoils. All the testing completed in this project was done in the Advanced Experimental Methods class at Clarkson University. First, I want to discuss the research objectives of the Aerodynamics and Wind Energy Lab, where the project originated. Our goal is to create a clean, sustainable energy available for consumers. To do this, we are working to reduce our key metric of cost per unit energy for small wind turbines. This project is specifically developed from my project within the lab to develop and design new blades to increase the efficiency of the turbine without increasing the manufacturing cost of the overall project. Essentially, this project will allow us to answer the key question of if a custom designed cambered plate airfoil is able to outperform the current blade geometry um, developed from the GOE 417A airfoil to make a more commercially viable product. The current blade set of the turbine has been in operation since October 29, 2019, and is still collecting data. It's using the GOE 417A airfoil, which is pictured at the bottom left here. Using the cambered plate airfoil has two purposes. The first purpose is the performance advantages in low wind speeds. Even as wind speeds increase, the cambered plate is not significantly outperformed by the traditional airfoil shape, as you can see on the right image. The second reason we chose cambered plate airfoils is the manufacturing cost of the blades designed this way. So far, two methods of blade production have been utilized. First, the carbon fiber layout method, performed by Vistex, and secondly, an aluminum stamping method that was developed in-house. Aluminum stamping has shown to reduce production costs of the blades by over 90% compared to both carbon fiber and traditional milling techniques, which really proves that cambered plates are a good option. This study is unique in the fact that it focuses on low Reynolds number airfoil design, whereas most airfoil optimization studies focus on high Reynolds number optimization. Preliminary studies were conducted using a design tool developed in MATLAB in conjunction with an open source airfoil analysis tool, Xfoil. About 200 airfoil iterations were tested at the lowest end of the turbine operating range, a Reynolds number of about 80,000, and only one of the custom airfoils outperformed the current airfoil, the GOE 417A. This can be seen in the bottom graph here. The results from this prompted further investigation into that airfoil, and the image in the top right shows this airfoil as it was tested through the operating range. The custom airfoil outperformed the GE 417A through the range with a maximum advantage of about 18%. This prompted us to look into this as our 401 project, and we wanted to validate this numerical testing in Xfoil.
As for the planning and organization of this project, we had a fairly easy time organizing the experiment. The only real issue we had to deal with was getting our airfoils manufactured by the makerspace, which was an issue just because a lot of the things were being 3D printed throughout the university, which led to a little bit of a backup within the makerspace. Once we were able to acquire the printed airfoils, the only other thing that we had to organize was finding time in the wind tunnel to do our testing. Matt was a big help with this and made it very easy on us to get in there and get the time we needed. For the budget of this project was very cheap, costing us nothing. The university covered the cost of 3D printing materials through our personal budgets that we have, and there were no further costs incurrences on anyone. The only other minimal cost would have been energy to run the wind tunnel, which the university already pays for. The wind tunnel running for less than 30 minutes would have been a negligible cost compared to the scale of the university's energy consumption. This experiment was deemed by us as a very low-risk experiment, the only major risk being the high wind speed of the tunnel and fast-moving parts in the wind tunnel. The only necessary safety precautions taken were to wear safety goggles and earplugs if necessary around the wind tunnel. The only other precaution taken was to keep clear of both the intake and the output location when the wind tunnel was up and running. For our experiment, we had to test our two different airfoils at 5 different angles of attack and 3 different wind speeds. The first hurdle to tackle was getting our 3D airfoils designed and manufactured. Our airfoils were designed in SolidWorks off of the two different 2D airfoil designs for the GOE 417A and our custom airfoil with minor changes from the GOE. Once they were designed in SolidWorks, we decided the easiest way to get these manufactured would be to 3D print them in the makerspace. We had minor issues getting the prints completed, but once we had them done, this proved to be a very easy way to do this. From there, once we had our airfoils manufactured, it was on to the testing stage of our experiment. Once we had some time with the wind tunnel secured for our testing, it was fairly simple and straightforward. The first step was to run the wind tunnel without an airfoil in it to get our 0 readings from the wind speed. From there, once we have the 0 readings, we insert one of the airfoils and turn the wind tunnel on. We start at 6-degree angle of attack on the airfoil and take the readings down for the lift acting on the airfoil. The angle of attack was then increased to 7 degrees and the reading was taken again. This was then done for 8, 9, and 10-degree angles of attack. Then the whole process was repeated with the other airfoil, and then once the other airfoil was done, the whole process of testing with each airfoil was then repeated to analyze the drag on the airfoils. This whole process in total had around 72 trials, which went rather quickly once we developed an efficient process for testing. The 0 value first gathered was taken multiple times and throughout the experiment to improve the integrity of our results. Once our results were gathered, there was some minimal conversion between the gathered results and millivolts by using the calibration curve to find the equivalent forces that was experienced by the airfoils.
As previously discussed, the primary outputs or independent variables of this study are lift and drag forces. To optimize turbine airfoils, drag must be minimized and lift must be maximized. Therefore, higher lift-to-drag ratios represent better performance. Comparing the lift-to-drag ratios of the custom airfoil to that of the GOE 417A airfoil as a percentage is a convenient way of analyzing performance differences. At all three Reynolds numbers, 80,000, 200,000, and 300,000, the custom airfoil had a higher lift-to-drag ratio, and that was even taking into account the varying angles of attack. At an angle of 6 degrees, the lift-to-drag ratios were highest. We saw performance gains of about 7 to 12% when compared to the GOE airfoil. As angle of attack increased, though, the lift-to-drag ratio started to drop off, resulting in less performance. But still, they remained higher than that of the GOE airfoil at all points. While lift-to-drag is a primary metric used to analyze blade performance, isolating lift forces allows us to see if the custom airfoil has other low Reynolds number applications where high lift is desired. Here we can see that the custom airfoil achieved percent lift values of up to 142 to 156%. As seen previously, however, performance decreases with increasing angles of attack. Overall, the custom airfoil outperformed the GOE 417A in terms of both lift-to-drag ratios and lift alone. Using zero-order uncertainty of the force balance in the LabVIEW 5, as well as error propagation, an error of 7% was determined for the data points obtained. This means that the lift-to-drag ratios of the custom airfoil aren't necessarily higher than the GOE airfoil at all attack angles. That being said, lift is still considerably higher at all angles, even when considering this uncertainty calculation. It's worth noting that relative comparisons of the data were used to eliminate error and assumptions like surface roughness.
Overall, this project was very successful. The wind tunnel testing appears to have validated the results of the preliminary numerical simulations, and it shows that cambered plate airfoils can be improved, and more specifically, that the GOE 417A is not the best option for use on the Clarkson University ducted wind turbine. Additionally, the high lift performance of the custom airfoil suggests that the custom airfoil may be useful in other low Reynolds number applications, such as the wings of micro-air vehicles. However, evaluating that directly was outside of the scope of this project. Moving forward, additional analysis tools will be utilized. Analysis will eventually switch from 2 dimensions to 3 dimensions using an in-house code known as MRotor. If MRotor yields positive results, fabrication of new blades via the stamping method discussed earlier will begin. From there, real-world performance validation will begin on the testbed turbine. Lastly, we would like to acknowledge all the people that helped us throughout this project. This project would not have been possible without the efforts and supports of the Aerodynamics and Wind Energy Laboratory, specifically Dr. Kenneth Visser. Additionally, we would like to thank our TA, Matt Turner, and the Makerspace for assistance throughout the project.